right. So let's take a look at exercise 5. So find the point on y equals root x closest to 20, comma 0. Okay, there's a question. This closest, the EST, that's the thing that's trying to give away what we're minimizing or maximizing. Closest means small distance, right? So how small can the distance be? So in other words, minimize the distance between what? The point on the parabola and this point, 20, comma 0. The point on the parabola, by the way, that point, we'll label that point as just x comma y. So y equals root x is a half parabola, sideways half parabola. So this is y equals root x, and then 20, comma 0. Sorry, not to scale, but there's comma 0. The y coordinate is 0. So there's going to be a point here. I mean, every point along here, we're calling an x comma y, but we want to know if I picked, what point would I pick on this shape so that the straight line segment is as short as possible. Okay, so we want to minimize that distance. The distance, so the point x comma y here has to satisfy the equation. That's the only way it's on this curve. So the thing is, if we apply the distance formula here, we'll have x minus 20 quantity squared plus y minus 0 quantity squared. We'll just not write the minus 0. Okay, that's the distance itself. It turns out that the square of the distance, so square this, squaring, just this square undoes the square root. We just end up with this. Okay, if you graph this and this in the graphing calculator just for a moment, you'll notice that the same x value that makes this small will also make that small. All right, so we'll minimize this instead. Oh, sorry, there's two variables now. We're going to have to substitute. Remember, y equals root x. So we could rewrite this as x minus 20 quantity squared plus y is root x. Oh, there's still a square. And then the square and square root into each other. So x minus 20 quantity squared plus x. This is good, because here I wanted to differentiate this thing, but it had two variables. So in optimization, you got to get down to one variable. Here it is. So this is s still, written with one variable, and we can now compute s prime. We could have written an s of x here if you want for the first time. Differentiate this. You can either use algebra and do x minus 20 times itself first and then differentiate, or here I'll just use the chain rule. It's not too bad. So 2 times the inside raised to the first, I won't write that, times the derivative of the inside. The derivative of x minus 20 is a 1 anyway, right? 1 minus 0. So times a 1, but I won't write even the times 1. Plus the derivative of x is 1. Now this is what we set equal to 0, right? So we'll set 2 times x minus 20 plus 1 equal to 0. So let's see, this is 2x minus 40 plus 1, so minus 39. Add 39 to both sides. X is equal to 39 halves. Now what we need to do is check. Here's s prime of x. Let's look at s double prime of x. The second derivative, okay, 2x minus 40 plus 1. So the second derivative is just 2. And if we plug in, whoops, function was called s. It's in the habit of writing f, I'm sorry. So s double prime of this number is still 2, right? So we just had to take this formula, and everywhere we see an x, plug in 39 over 2. There was just no place to plug in an x. So we'll just do that. Okay. Now this positive value of the second derivative means that if we were to graph the s function, right, s-axis, y is s, x-axis, then you'd see, maybe we should call it y, okay, just because there's already a y in the problem. The point is this second derivative positive means that the graph is going to be concave out everywhere. I'm not quite sure exactly what it looks like off the top of my head, but it's something like this. If you were to graph this, right? And so the point is, you have concave up everywhere, but then the moment when the derivative or the slope is 0 is at this x value. So at this x value here, 39 halves, that's the smallest possible value of s, and that also ends up being the smallest possible value of this. Go ahead and graph this. Graph in a calculator root quantity x minus 20 squared plus root x squared as a way to replace that. And you'll see that the dip occurs at the same x value, 39 over 2. 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 Okay, so we're saying here, because of the positive second derivative, concave up for the original function s here. So s has a local min at this x value of 39/2. So then we know that that's the right value of x, but the question, what was the question? Oh, find the point. Find the point. A point has an x and a y coordinate. That's the correct x coordinate. So the point, the closest point is, well, x comma y. So x coordinate is 39 halves. What about the y coordinate? We know the x value is 39/2. We can get the y value by, oh yeah, this. The y value is the square root of the x value, at least all along this curve it is. So we have root 39/2. Let's also in this segment take a look at exercise 6, which is another closest point kind of thing. So exercise 6, find the point on, let's see, what is this here? Y equals 5x plus 2, closest to the origin. Okay, so now we still want to minimize a distance. So d is the distance from a point that we'll call again x comma y on now the line is a y equals mx plus b to the origin. So the distance between this point and that point using the distance formula should be x root x minus 0 quantity squared, we just didn't write the minus 0, plus y minus 0 quantity squared, I just didn't write the minus 0. Okay, there's our distance between the point on the line and the origin, but this thing d is more challenging to differentiate. Again, there's two variables right now, but the square root means there'd be an added chain rule in the process of differentiating. So instead of minimizing d, let's minimize instead s. The same x-y combo is going to minimize s as it does. The same xy which minimizes s will also minimize d. And the same xy which minimizes d will also minimize s. Just kind of a property about squares and square roots. So let's minimize the square, s being the square of the distance. The square undoes the square root, and so we'll minimize this. But we want to, if this is what we want to minimize, differentiate this stuff equals 0. We can't differentiate yet with two variables. So we got to substitute. Right? So x squared plus for the y, up here 5x is 2 quantity squared. Now this is all in one variable, and now we can find a derivative of this 2x plus, by the chain rule, 2 times 5x plus 2 raised to the first times the derivative of the inside, which is 5. So if we go ahead and set this equal to 0, 2x, what's the, 2 times 5 is 10. Let's take care of that first. Set this equal to 0, we'll have 2x plus 50x plus 20, yeah, 50, 20, yeah, equals 0. So we'll have 52x equals negative 20, x is equal to negative 10. Well, I'll just leave it as negative 20 over 52. Negative 20 over 52. Okay, that, if we can compute the, well, this is also s prime. So from here, let's compute s double prime. Oh, this is also s double prime. It's just less work to not have to deal with the parentheses and all that. So if this is s prime, it's just another way of writing s prime. It's really a 52x plus 20, and so the derivative is 52. And so then s double prime of this x value is still 52. Positive second derivative means if you graph s, right, if you were to graph this right here, you'd have concave up the whole time. So we are, concave up means we are finding a local minimum, right? So S has a local min at this x value, at x is equal to negative 20 over 52. So then you can go back and say, oh yeah, find the point on the line. So a point has an x and a y coordinate. We know the x coordinate should be negative 20 over 52. What's the y coordinate got to be? Well, it's a point on the line, so it has to satisfy this. So to get the y value, take this known numerical value of x, and we'll have 5 times that number, negative 20 over 52, plus 2. Okay? So there's x comma y, parentheses.